Boleh jam 8 ya, Prof ya? Sorry.
Boleh.
Oke. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Terima kasih Prof. Herman eh, bisa hadir pada lecture sesi kedua pagi ini. Sesi kedua ini tampaknya sangat menarik karena sudah masuk dalam topik-topik advance. Terima kasih pada semua Bapak, Ibu, dan mahasiswa yang bisa join this morning. We will continue session 2 of 2 sessions lecture di dalam ajang profesor program Universiti Brawijaya. Terima kasih pula untuk para pensyarah dari seluruh Indonesia boleh hadir pada pagi hari ini. Kemudian acara hari ini, pagi ini adalah secara lecture sesi kedua, kemudian nanti dilanjutkan dengan tanya jawab di ujung lecture. Kemudian ada presensi ya namanya, ada presensi. Yang tidak lupa adalah nanti ada foto bersama yang minggu lepas kita terlupa. Kami persilakan Prof untuk dimulai. Terima kasih, Prof.
Baik. Assalamualaikum warahmatullahi wabarakatuh. And very good morning. Thank you very much, Pak Wee, as a moderator for today's, we can say, sharing session. First of all, can you see the slide?
Yes, Professor. You can see it.
Prof. Ya, Prof.
Okay. So, Assalamualaikum and very good morning to all professors, associate professors, lecturer, doctors, students, and researchers from anywhere you came. So, today I would like to continue my topics on the flux switching machine. But this time, I will focusing on the design and performance optimization, which is, we can say, it's from concept to application. Basically, we have understand in the previous lecture a few concepts, the basic fundamental of flux switching machine operation. So what we can see now in the application of in terms of the electric machine itself, as well as for our daily life. So this is about myself again. I was born in 1978. I'm 47 years old this year. So I got my Bachelor of Electrical from Universiti Malaya in 2001 and Master from Quito. Quito is actually the previous name. PhD in Electrical from Nagoya Institute of Technology, Japan in 2012. And then I got my Professional Engineer certificate in 2016. And as a part-time imam in Mosola in my area. So I also possess a diploma executive in imam professional in 2022. So the goal for discussion today is to provide an understanding of the design principles, development process, and performance optimization technique of flux switching machine, which is from fundamental concept to the practical application. So this is about the subtopic that I will discuss today. I have about 70 pages, 70 slide pages. So all about is about 8 subtopic, including introduction, general design procedure, FEM design using GenMake Designer, performance analysis, design optimization, fabrication testing, and I will share also my experience in UTHM and several machine design that have been established here. And also I will summarize and give a conclusion. So as an introduction, I will divide into three main parts. That is definition, the quick revision of the previous discussion on flux switching machine, and also what is the motivation for the researcher to do research on flux switching machines. So as we can recall, the flux switching machine definition is a brushless AC machine where both the armature winding and excitation, either PM or field excitation, are located on the stator. So this is the very basic definition, the idea in which all the main flux sources, including armature winding, are located on the stator itself, while the rotor is just a simple salient iron structure. So rotor will be the single piece simple iron that can rotate robust under high-speed application. So the key idea of flux switching machine is nothing but the flux linkage in the armature winding switches between stator tip as the rotor rotates. So that's why the term flux switching happen when the flux linkage in the armature winding switch the polarity as well as in the stator and the rotor itself. So the basic structure, okay, please recall this one, basic structure of a flux switching machine. The stator houses all winding, including armature and DC field excitation or permanent magnet. It can be either salient or segmented condition. And the rotor itself, it has a tooth-steel lamination with no winding or magnet, and can be either salient or segmented structure. So a quick revision again, just for our recap. So flux switching machine can be divided into permanent magnet, FSM. Okay, as we can see here, when we call permanent magnet FSM or PM FSM, the main flux sources is come from the permanent magnet itself. You can see in the green color is the permanent magnet. Okay, we have here 12 numbers of permanent magnets. And then another flux sources is the armature coil that is wounded in blue color. So please recall that in order for the motor or machine to operate, there must be at least two flux sources based on the fundamental of electric flux linkage that happened in the previous, we have discussed in the previous discussion, previous session, in which in order for the energy to be converted from flux to the movement, so there must be two flux sources in the case of electric motor. Minimum, it must have two flux sources. So for the case of field excitation here, so we have two flux sources also that is first come from the DC field excitation. This is in the pink color, and also we have the AC or armature flux linkage that's come from the armature slot itself. So now we have two flux sources here, so that the idea on the energy conversion that will make the movement happen is there. And then we have the hybrid excitation, okay, in which the combination of the permanent magnet, okay, and also the field excitation as well as the armature coil itself. So in here we have the how to say, the variation of the flux linkage, flux sources, in which we can control the flux strengthening and flux weakening of the machine itself. So please put in your mind that the stator itself, you can see stator itself consists of all the flux sources, and the rotor consists of only single piece of iron for all the three cases. So this is actually the uniqueness of the flux switching machine. And then the motivation for the researcher to do the research on flux switching machine. First is high torque and power density. Because of its utilized stator and rotor saliencies with concentrated winding, so it leads to a strong magnetic coupling between the stator and rotor itself. So we can expect that high magnetic flux density is there. And also because of that, it's produced high torque output per volume and consists of compact design and suitable for EV and aerospace. Why EV? Because EV is like the transport that are emerging now. So to have a electric motor in EV, so it must have a small design, compact design, and also lightweight as well. And second thing is the robust and simple rotor structure. Okay, rotor typically made of limited steel, no PM, no winding. So the key word here, or key point here, is that it can be reliability applied at high speed application with no rotor losses. And the third motivation is high efficiency and fault tolerant operation. Of course, when we have a compact rotor, we have a better thermal management because of all active part allocated on the stator itself. and as well as we can control the magnetic through the flux strengthening and weakening. And then we have also reduced the copper and core losses that produce high efficiency, as well as easier cooling and maintenance stuff. Okay, now I will go on the general design procedure that can be divided into two parts. There is initial design specification and the suggested software or final element method or magnetic software that we can use to design and apply the analysis. So basically, when we want to design electric machine, I think the general design procedure is very general and it can be applied for all type of electric machine. But here I will focus on the flux switching machine itself. So first of all, if you want to design a machine, we have to know what is the power rating that we want. So in example, for this case, I use 1 kilowatt power as the power rated power. And I will choose the permanent magnet flux switching machine. And then we have to choose also the speed. Okay, in this case, we can choose 3000 RPM, or we can use low speed as such as 1500 RPM. So because of that, when we have the power, we can calculate the torque, okay, using this formula, torque equal to P over omega. So we can get about 3.18 Newton meter torque. And this is something that related with the circuit, with the armature current density. So either we can use air cool, fan, or water jacket itself. It depends on the application itself. And the most important is the target efficiency should be more than 85% for the case of permanent magnet flux switching machine. So when you have the very basic specification, then we need to choose the topology and the slot pole combination. So as we know that in the stator, it carries both winding and PM only. Okay, the name is PMFSM, so it must have two flux sources. First is the armature winding, and second is the permanent magnet that carries the flux. And then the rotor is serial with no permanent magnet. So from this combination, we can recommend the number of slot and pole is 12 slot 10 pole or 6 slot 4 pole. So how we got this 12 slot 10 pole and 6 slot 4 pole is nothing but from the formula. Okay, we can have it here, this formula, and S is the number of stator slot. Okay, let's say we want to produce a stator slot of 12 slot, yeah? Or we can produce 6 stator slot. Okay, in the case of three-phase, we need to have the multiple of 3. So it either can be 6, 12, and then 15, 18, and so on. So we can calculate the number of rotor poles suitable here, NR. NR is the number of rotor pole. So from this formula, NS 1 plus minus Q over 2Q. So Q is the phase. For single phase or three phase, we can simply change this Q here. So for the case of NS equal to 12 slot, okay, the most suitable number of rotor pole is 14, 10, 16, 8, and so on. Okay. While for the case of 6 slot of stator, the number of rotor suitable varies from 7, 5, 8, 4, 9, and 3, and so on. So for the case of this, okay, because we have a combination of 12 slot, so the most, suitable combination is 12 slot 10 pole and 6 slot 4 pole here. Okay, because the stator itself have a large number of pole itself when compared to the rotor itself. So this is the example of 12 slot 10 pole of the PMFSM. We can see there is a permanent magnet here. Okay, the armature coil here, and also the number of rotor pole here is the number of 10 rotor poles number. Okay. Okay, then when we have the specification, we have the number topology and slot pole combination, then we can do the sizing. We can calculate the sizing. What is the suitable size of our motor itself? So for this, we can use the formula P equal to C naught times D square times L times the speed. Okay, and C naught is usually the output coefficient. That's between 20 to 40 kilowatt per meter cube radial per second. So for C naught is equal to 30. So this is we just choose the C0 equal to 30 and the speed of 50 RPS, power is 1 kilowatt. So we can calculate D and L. D is the diameter of our machine and L is the stack length of the machine. So from here we can find D equal to 110 and L equal to 55 millimeter. So this is the example of the PMFSM with having a diameter of the machine, which is outer static diameter is 110 millimeter, and we have the stack length or axial length of about 55 millimeter. So this is just the preliminary design procedure that we are having until now for our machine. And then the next step is about the magnetic design, that is to understand the flux path and the magnet itself. So first of all, for the electric machine to be rotated, it must have an air gap. So the suitable air gap is about 0.25 to 0.6 millimeter with 1% tolerance in our lab. For the small machine, we use 0.25 as a minimum. And for the large machine that is above than 100 Newton meter, we will use about 0.5 millimeter of air gap. Okay, and the PM itself is embedded in stator teeth in segment and use alternate polarity. So alternate polarity means that in some case the flux direction of the magnet is like this, and in another one is in opposite direction, is like this. So it will be in alternate polarity, alternate position. So why? Because it can make a complete flux like cycle through the rotor itself. For example, this one magnet come from here, and they can flow to the rotor and come back to the stator. Okay, and go back to the magnet itself to make one complete cycle. And type of magnet can we use is neodymium ferrum boron. Sometimes we can say that neodymium iron boron with the grade of N35 to N52 for the highest magnetic flux density. And then the thickness, it depends on our design itself. Okay, and we should put the target flux density in the stator about 1.3 to 1.6 Tesla, while the air gap flux density is about 0.6 to 1 Tesla. So from my experience, okay, I can say that the rule of thumb for machine designer, we can use the PM volume in the ratio of 1 to 25, which means that if we are using 1 kilogram of permanent magnet, so the total motor weight itself must be about 25 kilogram. Similarly, if we are using about 100 gram of magnet in our motor, so we can use about 2.5 kilogram of the total weight of our motor itself. And then when we identify the magnet and flux linkage itself, then we can go for the winding electrical design. Okay. So in the case of winding, for all the PMFSM, we can use the concentrated tooth wound coil. It can be simply shown in this figure. So concentrated means the winding is like this, okay, in one slot area itself. So this is like the slot of the stator tooth. Okay, you just wound all the winding all around the stator tooth itself. And the number of turn, you can use the slot size and wire diameter to calculate the number of turn. For example, if you have a slot size like this, okay, this is the slot for your coil to be inserted, to be wounded. So let's say this size is about 100 mm, okay? Let's say the area of the slot is 100 mm, and you are using a 1 mm square size of the coil, okay? This is the coil size for 1 mm square. So the slot area is 100 mm square. So practically, if this area is 100, okay, if the area is 100 mm square and the coil size is 1 mm, so ideally we can put 100 number of turn inside the slot itself, because the area size is 100 mm square and the area of the coil is 1 mm square. So in ideal case we can put 100 turn. But in the real case, no, we need to put a fill factor, because in the case of real application, okay, we need to slot in all the number of turn or coil like this, okay, like this condition. So we cannot fulfill all the area with 100% coil inside the slot. So because of this, researcher has made some rule of thumb that basically for the case of the slot, so only half of the slot will be full, okay, will be fulfilled 100% with the coil itself. So this is what we call the filling factor because of the air gap and so on. So filling factor that is suitable for the machine is about 0.4 to 0.6 for manual winding and 0.7 for machine winding. And then the typical current density we can set about 5 to 10 ampere per meter square for small machine. It can be set up to 30 ampere per meter square, depends on the compactness and the what we call system that you can use to eliminate the heat from the machine itself. And the frequency depend on us up to the speed that we want to use. Okay, we can use the formula Fe equal to P times N over 60. P is the number of pole pairs, and N is the speed that we can set. So once we set all the parameters, all the design specification, including the winding, electrical, and so on, now we can design our machine using the finite element method of finite element magnetic software. We can use 2D or 3D FEM, and initially we can simulate the flood path, the clogging or torque ripple, the KMF, flood density, flood line, and some losses. Okay, through my experience, the suggested FEM software that can be used to design electric machine is a JMAC Designer. Okay, JMAC Designer is the software that is provided by the Japanese industry. So when I was in Japan, so it's called a JMAC Studio. Back in 2012, and start from 2014, it's changed to JMAC Designer. Until now, in our lab, in Iteration, we still use a JMAC Designer. Professional license, we have about 13 license in here. Okay, we can also use the ANSYS software. Okay, and also we can use the COMSOL multi-physics and also Altair Flux, electromagnetic, electric, and thermal analysis to design our motor itself. So for ANSYS, I have some experience with, I can say the another researcher in another university in Malaysia also use ANSYS, and also the COMSOL itself. I have a bit experience in using this when comparing the design from JMAC and the ANSYS. So this is the interface of the JMAC Designer. Okay, I'm not sure whether in Brawijaya you have this software or not. But to be familiar with this software, it is very simple software. Okay, it has two control part. That is the project manager and CAD drawing in the left part, and also the material selection and condition setting in the right part. So in here, in the middle, we can use the how to say, to draw the design and to set everything inside the rotor part itself. It's same like the basic of this design is same like the AutoCAD. So first you need to draw all of the part itself, and then you have to merge it, and then you have to set the condition and so on. So now I will go to subtopic 3, FEM design using JMAC Designer, because since 2009 I'm using JMAC Studio and then changed to JMAC Designer until now. So I will go to design methodology, geometry editor, and some JMAC design setting itself. So basically, when we want to use the JMAC Designer, it consists of two parts. First is geometry editor, as I mentioned before. Geometry editor is nothing but we need to draw all the parts of the electrical machine. We need to draw the stator, the rotor segment, and then the armature coil, the PM, and so on. So, and then we have to make sure the region has been created successfully. One is completed, and then we can go to the JMAC Designer, that is to do the setting and material setting and the circuit and so on. So inside JMAC Designer, we will do the material setting. Okay, what is the material used for stator, for the rotor, PM, and so we can add the circuit and link the coils to all the parts that we have set in the geometry editor, and we can set the condition as well as the mesh properties. And then we need to check the sinusoidal of the flood linkage at 120 degree phase difference. This is nothing but when you have a three-phase current source like this, then you need to make sure that the the phase shifted between each phase is 120 degrees. Okay. This is a bit detail on how to do the part of the electric machine using a geometry editor. Okay, first is rotor design. So in rotor design, we need to draw a fraction of the rotor itself. A similar concept when you use the AutoCAD. And then we can create the region, okay, mirror the application of rotor, and then finally we can do the radial application to make a complete rotor. In this case, I'm using example of four-pole rotor. Okay. Then we can start to design the stator. The same process, draw the fraction, create the region, mirror application, and then we can do the radial application. In this case, initially the stator have a C-core type. So when we do the radial application, now the stator become the single piece stator. Okay, with consists of 6 slots. Next, armature coil design, same process. Do the fraction of armature coil, create region, mirror application, and then radial application of the armature coil. And finally, the permanent magnet design. The same process goes until we have the radial application of permanent magnet. So finally, we managed to design the complete set of 6-slot 4-pole permanent magnet synchronous machine. Okay. This is another example of a 12-slot 10-pole PMFSM complete design. So first of all, we are using the segmental stator, E-core segmental stator, and then we do the application to become 6 times E-core stator, and then we do the 10-pole modular rotor, and then 6 times permanent magnet, 12-slot armature coil, and finally the shaft and the rotor up. Okay, this is the result from the geometry editor itself. Then we need to do the setting. The setting is nothing but to change, to select the material type. For the case of rotor and stator, normally we use Nippon Steel 35H210. Okay, for rotor, we need to set the motion, rotation, and top nodal force. Okay, 35H210 is nothing but thickness is 0.35 mm, and 210 is 2.10 watt per kilogram core loss property. The density of the Nippon Steel is 7,600 kg per meter cube. For monomagnet, we are using Neomag 35AH. As I mentioned previously, we are using alternate and radial direction. The magnetic flux density is about 1.2 Tesla, corrosive force 932 kilaampere per meter, and density 7550 kg per meter cube. For coil, we are using the normal copper coil, using concentrated winding, and shaft and rotor hub, we can use the stainless steel, depend on the set of the number. That is SUST304, consists of 80% chromium and 80% nickel, and SUS316 consists of enhanced corrosion resistant when compared to the SUS304. Okay, this is a bit detail on the neodymium iron boron. Okay, this is the BH curve. I think you all are familiar with this graph. We can say that the maximum flux density is about 1.3 Tesla for the N42 NdFeB. Okay, and we can see that there is a knee point. Knee point is the point where the flux start to reduce drastically. Okay, it's about 900 kiloampere per meter. And the blue line is nothing but the normal operating region of the magnetic flux itself. This is also the setting that we can use in GEMAG. That is for different type of Neomag 35AH. We can see the density is about 1.2 Tesla. And the knee point here is varies depend on the temperature that we are using for our machine. Okay. And for the stator and rotor, we use the Nippon Steel 35H210, in which the flux density varies and can start to saturate at this point, in which the current is about 8,000 ampere per meter. Now we need to do a JMAC design setting in circuit and coil link. So the most important thing is here is we need to set the coil of UVWSF for the case of three-phase armature coil. So we need to have a current source, and then we need to have a star connection. So the connection or winding settings, circuit setting is like this. We have UVW setting, and then inside the source we can set the different type of polarity, either UWV or UVW itself. Then we can set the amplitude of the current, frequency, and also the U phase setting itself. So finally, we can get the circuit coil links as follows. Okay, from the JMAC design itself, when we do analysis, okay, we found that the U positive is in this polarity. Okay, the winding is like this, and then the U negative is winding is reverse like this. Okay, V positive winding is like this, and then V negative is like this, and so on. Okay, so from the project manager part, we can set the FEM coil UVW, and we can identify the we can set the speed. In this case, we are using 500 revolution per minute of the rotor itself. Another setting that we can do is the magnetic transient analysis. Step control 37 is nothing but to divide the one electric cycle to 37 parts. Time, it depends on the frequency. Division 36. Stack length depend on the size of the machine that we want to design. And then mesh, we can use the slide mesh for all parts. For the motion, we can set rotation, and for the torque, we can set the Nodal force. This condition only happen on the rotor itself, rotor as well as the shaft. Okay. Next, once we complete the JMAC design analysis, then we can do the performance of the open circuit test and also the short circuit test. For the open circuit test, basically we want to identify whether our three-phase flood linkage is generated successfully. So for the case of this design, okay, we have successfully generated UVW flux. Okay, we can say that almost sinusoidal flood linkage waveform. Okay, basically because we are having three different six coil, coil U plus, U minus, V plus, V minus. Okay, and W plus, W minus. So initially we don't know. Okay, initially when we start to design, we don't know which coil is U plus, which coil is U minus, which coil V plus, V minus, and so on. So the very basic step that we can use is we can do the armature coil test itself. So we just put the armature coil in the same direction for all cases. Then we run without having a continuity between them. So then we run the rotor, and we can see the flood linkage itself. So from the condition of the flood linkage, okay, some flood linkage might be opposite, might be in reverse direction. So from that we can prepare, we can change the polarity of the UVW phases. So finally, it will generate a three-phase flood linkage as shown in this figure. Okay, other analysis that we can do is flood line, Coulomb torque, and so on. This is the example of the flood distribution that happened inside the machine itself. You can see that the maximum flood density generated is about 2.5 Tesla, which is beyond our target. And then this is an example of another open circuit test analysis. So in here we can see 6 different types of PM FSM. So first type we have the sandwich PM in between of the rotor stator pole itself, and we are having a 10 pole of rotor. Then we have a still sandwich, but we have a 14 pole of rotor, and then we have a V shape 10 pole, and then we have a V shape 14 pole. And then we have a multitude PM 10 pole and multitude PM with 14 pole. Okay, this is just for the sake of comparison. So when we do the analysis, we can see that the highest flux generated is for the case of 6 slot 10 pole multitude permanent magnet FSM. So this is the highest flux generated, which is about 0.06 Weber. When compared, the lowest one is this one, the green one, that is 6 slot 14 pole multitude SS FPM. Then we can also check the induced back EMF by using the flux linkage generated. So because of 6 slot 10 pole multitude is giving the high flux linkage, so EMF also is generating the highest EMF. And then we can look at the Cogging torque itself. You can see that the Cogging torque for the case of 6 slot 10 pole multitude is lower than the other Cogging torque from the other design itself. Then we can check the short circuit test. Okay, in this example, we are comparing the torque versus JA, is the armature current density. Okay, we can see that because of high flux from 6 slot 10 pole multitude, so the torque generated here is also the highest when compared to the others. But in terms of power itself, we can see that 6 slot 14 pole V shape, okay, in the blue color, is showing the highest power. The 6 slot 10 pole is showing the second highest power generated. Okay. In terms of torque versus speed characteristic, we still have 6 slot 10 pole multitude that give the highest torque speed characteristic. And then finally, we can do the efficiency analysis here. Okay. And we get average efficiency is above than 90%. Okay, until that, we have successfully designed analysis, and we can see the result of the open circuit in terms of the flux linkage, in terms of the flux distribution, Cogging torque, and so on, as well as the short circuit in terms of torque, power, and speed. Now we can go for the design optimization. Okay, I just will give you some introduction on various optimization method for electric machine, and I will focus on the deterministic optimization method to improve the performance of the FSM itself. Okay, through the literature, I found that most used design optimization is the stochastic or intelligent algorithm. This includes the genetic algorithm, particle swarm optimization, and also the DE itself, which is 35%. We can say that most of the researchers are using this kind of technique to improve the machine performance. And the second chosen optimization method is deterministic or classical method, which is about 20% of the researchers are using this, including me and my research student. So the basic idea is we can do the sequential technique. We can change the parameter one by one, and we can see the changes from the initial design until the final optimized design. What is happened when we change the rotor, stator, PM, and so on. Another possible and suitable design optimization is surrogate model-based method using the databases, and robust optimization using multi-objective is about 15% for both cases, and topology optimization by changing the shape and the material itself is about 10%, and last but not least, machine learning based method. Some of them are using Bayesian and some of them are using the AI method. So currently AI is very good. So in my lab, we also try to explore the AI method, and one of my I can say that coming soon PhD student will join our lab and will do the optimization using the AI. Okay, before I go through on the detail of deterministic optimization, okay, I would like to share you the finding that I did during my PhD. So in my PhD, actually, I tried to design electric motor for Toyota HEV, Lexus RX450H. In that case, I am using the IPMSM. Okay, IPMSM is the existing electric motor that has been employed in the Toyota HEV, and it is already run on the road since I think 2004, 2003, something like that. So with the capacity of 333 Newton meter of torque and power of about 123 kilowatt power. So what the Toyota company asked me is to find another suitable electrical machine that can replace the IPMSM currently exists in the Toyota itself. So based on the research literature, we found that the suitable candidate that can replace the IPMSM is the 12-slot 10-pole HEFSM. Okay, because it consists of 3 flux sources that come from the armature coil, okay, from the PM and the FEC. The most important part is that the FEC can control the flux of PM. It can strengthen the flux and for the high torque condition, and it can also weaken the flux so that it can operate at high speed condition. But initially when we designed this motor, so we found that the initial torque is 175 Newton meter, power 105.6 kilowatt, which is far from the target. Far from the target 53 and 123 kilowatt. Okay, then we look into the detail of the reason why it happened. So we try to plot the torque versus the JE, the field acceleration coil density, with respect to the JA. JA is the armature current density. So when we plot the graph, we can see that all the graphs are initially increased, okay, but it starts to reduce at some point, okay. For example, the case of this case start to reduce at the 10 ampere per meter square, and for the case of highest position, the JA equal to 30, it also start to reduce at this point. So when we look at the detailed flux distribution, we can see that this happened because of the negative torque direction that is happened when we increase the current density up to 30 ampere per meter square. That's why the torque from 182 is reduced to 176 at this case. So in order to remove or to reduce the negative torque, so we need to optimize the area that make the flux to reduce, okay, by using the deterministic optimization. First of all, we need to identify the parameter itself. So this is, I can say, the part of the state rotor, okay, and the part of the stator itself. So we identify the parameter of D1 is the rotor radius, D2 and D3 is the rotor pole width and depth, D4 is the permanent magnet height, D5 is the stator width, and then D6 is stator backyoke width, and also D7, D8 is the armature coil slot area, and last but not least, the D9 and D10, the air gap between the PM FEC and PM to the rotor itself. So when we have successfully identified this main parameter, so then what we do is we change this parameter from D1 to D10 repeatedly until the target torque and power of 333 Newton meter and 123 kilowatt is achieved. Alhamdulillah, successfully when we did all the optimization method, okay, from the initial design like this, okay, we have successfully changed to the optimized design like this. Okay, we can see a huge difference. The same size of the machine, but huge difference in terms of the part itself and the location of the size and so on. So basically, in the previous initial design, the initial torque at JE20, so we got 181 Newton meter. When we increase to JE30, the torque achieved of the torque reduced to 175, as I mentioned previously. But for the case of optimized design, at JA20, we got a torque of 280. When compared to 181, it's almost 100 Newton meter torque increment. And at JA30, we got the maximum torque of 334.5, and the power is about 1 to 9.6 kilowatt, which is successfully achieved the target. Okay, this is the just to see the result of the optimization. Okay, the top which is JE's condition. Originally, we have this blue line of the top, and then the final design is a red line. We can see that almost 90% improvement when compared from the initial. And then we have also the comparison of the top speed characteristic between HFSM and IPMSM. We can say that the proposed machine HFSM is having much wide area of torque speed characteristic, and it can be run at the high torque condition under high speed vision. We also identify the power versus speed characteristics. Okay, this is the comparison of power becomes we can say constant power at the high speed region when compared to the drop power in the case of IPMSM. Finally, we also check the efficiency and we analyze. We got the average efficiency is about 93%. Okay, once we successfully design and analyze and optimize the machine itself, so we are going to the final step, that is prototype, fabrication, and testing. All right, first of all, we need to do the mechanical design and CAD modeling. This is the work for the mechanical part essentially. So we can use the SolidWorks, AutoCAD, or CATIA to design the CAD software. We need to ensure the mechanical integrity, tolerance, and assembly fit. So this is the example of CAD design of Autoroto HFSM that we did in our lab in UTHM. And then we need to fabricate the stator, rotor, and PMSF. Stator and rotor, of course, we need to use the laminated core. So we can use the punching or laser cutting machine. Okay, in UTHM, we just use the outside resources to do the laser cutting and then to stack them and bond them to be one complete stator like this one. Okay, and for PM fabrication, we are using the neodymium ferrum boron. Okay, this is also we outsource from either from China or from the local resources. The shaft fabrication, we are using the stainless steel. And then we need to do the winding and part assembly. Okay, actually this is another design that I did in Japan. The design of field acceleration flux switching machine. Before I show you the comparison between IPMSM that apply in Toyota Lexus RX450H, and then I compare with the HFSM hybrid station. But in order to the Toyota company also how to say challenge us. Okay, why don't you remove all the permanent magnet itself and just do the flux sources by using the field excitation? So then we try to do it, and then alhamdulillah we made how to say optimized design like this condition. And then for this case, we have fabricated the stator, and when we also do the armature and FVC winding, and we also install all the rotor and shaft part inside the motor itself. Okay, during the assembly, we need to do a lot of things such as the rotor balancing. Okay, PM section is for the case of PM magnet. Okay, protective cooling and so on. And then we can combine the stator, rotor, bearing, housing, and covers to form the complete motor. Okay, this is the complete prototype of FFSM. That is successfully developed in Japan. So this is example of prototype of permanent magnet flex switching generator in UTHM. And also we have a prototype of field extension flux switching motor. This one also in UTHM. Okay, so once we successfully do the fabrication, so then we can focus on the testing itself. Okay, we can use the normal torque measurement system. We have a controller, dynamometer, speed up gear, torque meter, and the test motor. Okay, so this is the test motor itself. So this is the dyno. The torque meter is here. Okay, so we can check the performance in terms of back EMF, torque speed characteristic, losses, efficiency, and thermal and vibration. This is the result comparison of the back EMF between the measured, okay, and the FEM analysis. Okay, we can see that the results are in a good agreement between the measured and the FEM analysis itself. For the case of line-to-line or EMF voltage generated, and for the case of torque analysis, okay, torque versus current, we can see they have also a good agreement between the measured and also between the finite element method, FEM. Maybe there is slight difference here. We can see that about 5%, which is acceptable for the case of all electric machine design. This is another example that we set up the testing evaluation in UTHM. Okay, we measure the EMF voltage between the initial and measured, optimized, initial and optimized measured. So we can see that we have a good agreement between the initial, the measured and also the simulation itself. All right. Okay, I think this is the last part of my subtopic. Second last part before I go to conclusion. So I just want to share you a lot of design, a few design that we have developed in UTHM. Okay, I start with the FFSM for Toyota IGB that I've discussed previously. So the torque generated is 212 Newton meter, power 127 kilowatt with the efficiency of 91.9%. Okay, in 2014, this is when I did the design for the segmental stator, for electric scooter itself. So actually we improved from surface mounted PM to PM in between rotor to the segmental stator. So we have this, collaboration with one of the electric scooter company in Malaysia, that is Eklimo Sdn Bhd. So they are using the segmental stator in their electric motor itself. So the torque for each stator is about 25 Newton meter. So we have 1, 2, 3, 4 segment here. So we can generate a total of 100 Newton meter of the torque with the 10 kilowatt power. So the uniqueness of this machine is that we can add or we can reduce the number of the stator segment. They say if you want to increase the performance, we can simply add another segment of stator in between this slot. So from 100, it can become to 150 Newton meter. So another example that we have designed and successfully fabricated in UTHM is the permanent magnet fast switching generator. This is actually the collaboration in 2015 between the mechanical faculty, in which they want to generate the electricity using the biogas production. And then they have also the combustion chamber. And then our part is to just to provide the power turbine here. Okay. So we have successfully developed 400 volt generator with the power of 30 kilowatt and efficiency is 94%. And then in 2016, we have also successfully developed outer rotor hybrid extension FSM. So this is a unique design because we are using rotor in the outer part. Okay, you can see this blue color is actually the rotor. So the inner part, this is the rotor, the stator that consists of permanent magnet and also the armature. And we also use the hybrid excitation, okay, in which the rotor is still at the outside, and the inner part we have the permanent magnet, we have the armature, and we have the FEC as well. So what is the advantage of outer rotor? Is nothing but we can eliminate the transmission drive and the gear system of the current EV drive. So we can directly employ the outer rotor application to the wheel itself. So we can say outer rotor in wheel drive. So performance torque density 12.4 Newton meter per kilogram. Power density 5.9 kilowatt per kilogram. Efficiency is about 91%. Next, in 2017, we have developed the D square motor for electric scooter. So D square motor is nothing but direct drive, dual excitation. So dual excitation means that they are using the permanent magnet, also the DC field excitation. Okay, we successfully designed our motor like this, directly installed on the tire or in the wheel of the scooter. Okay, and this is we have a patent. For this one, we have a patent. In 2018, one of my students did a Salron motor. Salron means that salient, rotor, non-overlap winding. So it is the combination of salient rotor and non-overlap winding to become the Salron. And this has been applied to the boat, okay, electric boat. We have also patent for this design. Okay. And one of my students also did the Segron motor in 2019. He tried to, what we did here is we changed the existing induction motor in an electric fan to the segmental rotor non-overlap winding motor with the, this is a just small motor with the torque of 1.7 Newton meter and power about 270 watt. Okay, the idea is to remove the squirrel cage rotor inside the induction motor, okay, by changing the salient rotor for the high-speed rotation. And also we have improved the segmented outer rotor MFSM in 2020. Okay. So in this case, but the unique of this case is that still we are using the outer rotor. Okay. You can see this is the modular rotor of the rotor itself. And then we have the alternate teeth winding. Okay. Alternate teeth winding inside the stator itself. Performance itself, we got the top to 1.2 for 24 slot 10 pole and 241 for 24 slot 14 pole with power 30 and 35 kilowatt respectively. Efficiency average is about 91%. Okay, in 2020, okay, we developed Al-Siraf PMFSM. Al-Siraf is nothing but alternate circumferential radial flux. Okay, alternate circumferential radial flux PMFSM for electric scooter. We managed to get the torque of 47 Newton meter and power 12.9 kilowatt. This is very suitable to be applied for small electric scooter. And then we have also developed a dual stator HFSM for aircraft application in 2022. The idea is to separate the two stator. In the previous design, we only see one stator and one rotor. But for this case, we have dual stator, which means that we have the stator in the outside, and then we have the stator in the side. In between here is the rotor itself. Okay. For all the design here, okay, we can see that we have the stator outside. Okay, for example, this one we have stator outside, and then we have the stator inside here, and then we have the rotor in between of them. So the advantage is that when we have the stator inner with permanent magnet, so the heat from the permanent magnet can be released from the inner part, while the outer part of the stator is not so compact, so it can be placed with only AC and the FEC itself, in which we can control the losses and the thermal dissipation. Okay. For this case, we managed to get the torque of 160 Newton meter and 70 kilowatt power and 92% of efficiency, suitable for aircraft application. Okay, during the COVID time, also one of my students also successfully managed to do the hybrid excitation flat switching magnetic gear. This is not a motor, this is a gear when compared to the conventional mechanical gear. Okay, so the student is using the magnetic gear. So various type of magnetic gear has been successfully developed. Okay, for the case of rotating pole magnetic gear. Okay, and then hybrid excitation magnetic gear design 1 and also hybrid excitation magnetic gear design 2. Okay, and then 2024 last year, one of my students also developed the molar rotor PMFSM for the scooter itself. Okay, this is the various design that has been developed, and then the performance of torque and power is 53 Newton meters, 7 kilowatt with 91.7% efficiency, suitable for Honda electric scooter. Okay, now I think I can about to finish my presentation. So what can I summarize from today sharing is that first of all is the systematic design procedure. Okay, we need to have a systematic design procedure, and we need to have accurate geometrical parameter identification that offers the foundation for achieving optimal performance in electric machine development. Then we need to use the finite element modeling. Okay, basically in my lab we are using JMAC Designer. Okay, to provide an effective and precise platform for electromagnetic field analysis and design validation. And then we need to do the comprehensive performance analysis to confirm the accuracy of the initial design assumption and verify key operating characteristics. So this is nothing but we're going to identify that our design motor, our motor that we design is can be rotated. The flat linkage itself has been shifted between the phase of 120 degree, and then the armature flat linkage can be reacted with the permanent flat and so on. Next, the advanced design optimization technique significantly enhance overall machine performance, potentially achieving up to twofold improvement in torque and efficiency itself. So it depends on the condition of the motor itself. Okay, basically in my experience, the maximum performance that we can get is up to double. Let's say the initial torque is 100%, 100 Newton meters. So we can, after the optimization, we managed to get double to become 200 Newton meter. Finally, the prototype fabrication and experimental testing successfully validate the simulated result, demonstrating strong correlation between analysis, numerical, and practical performance outcomes. So as a conclusion for today, I can say that the flat switching machine offer high torque density, robust rotor structure, and high efficiency, making them a strong candidate for next generation electric drive application. A systematic approach from analytical design, FEM simulation, using JMAC to optimize and prototyping is essential to achieve the desired performance and reliability. And my final conclusion here is continuous research and innovation, such as those carried out in UTSM Electric Machine Design Group, are key to advancing FSM technology from concept to real-world application. So I think that's all for my presentation today. Thank you very much. If you have any question, you can simply ask. Inshallah, I will try to answer my best.
Terima kasih, Prof. Luar biasa ini. Karena ya banyak hal yang belum kita ketahui sebelumnya. Monggo para partisipan kalau ada pertanyaan.
Di dalam chat ada
Iya, ada dua, Prof. Ya. Yang pertama, apakah sudah in mass production? And what is the challenge to replace existing electrical machine such as induction motor and PLDC? From Afikah.
Oh, okay. Question is, did FSM has been applied in any machine application? I mean, real application,
Yeah.
in mass production? No. The very simple answer is no, because to replace the existing machine to the new machine, they require a lot of huge of cost because they need to do all the machine structure and then the mounting of the machine. I don't know, but basically the reason is the cost, because when we compare the cost between the FSM and induction motor itself, induction motor is very widely used. We can see that 46% of the electrical equipment are using induction motor. Induction motor is very cheap. It can be simply direct plug in into the stator, into the normal flux source in our home. So I can say now is quite difficult, but in future, okay, when the EVs, because this specific electric machine of FSM is focusing on EV, because as what I did in Japan, we did it for Toyota HEV, and back to Malaysia, we did in some design for electric scooter. So for that case, I think it's reliable, but until now, still not yet. We have mass production in the world itself.
Okay.
I think that is my answer.
Ya, semoga memuaskan Puan Apikoh. Yang kedua, I have a question which key design parameters most significantly affect the torque and efficiency of the flux fixing machine and why?
The key design parameters, okay, in terms of optimization, okay, let's say you want, we have the initial design, so then we have the performance of the initial design. So if you want to increase the performance, so like what we did in utilization, okay, we just simply using the sequential technique of the deterministic approach. So from that, we can identify several parameters. Let's say the rotor parameter itself, we have 3 parameters of rotor. Then we have 2 parameters of stator, 2 parameters of armature itself. So from my experience, the key parameters that affect significantly is the rotor. Okay, initially we have to set the split ratio of the rotor with the stator outer diameter is about 70%. So then when we play around, okay, with that, in some cases we might achieve about 85%. And if we tabulate the graph, for example, let's say the initial is 100 meter, 100 Newton meter torque, and then the final one, the optimal one is 200 Newton meter. Then when we tabulate the rotor itself, how much torque it increased when compared to others, I can say that rotor can give about 40 to 50% increment out of all the other parameters. That is from my experience. I don't know if you guys have another experience on that. I think that's all for my answer, Pak Willy.
Ya, terima kasih Prof. Mungkin yang direct question.
Ya, kalau ada dari
Ada dari
Baru.
saya. Okay, Prof. I want to ask. I want to know what is your suggestion to improve the power to weight ratio of the machine generally. How to do it?
power to weight ratio.
Power to weight ratio. That's the first question, and the second is related to the questions from other participants. Can we build the machine, probably FSM or the induction motor? Can we build it ourselves? And if we must build it ourselves, what the facility we need? Or what any machine we need to build it ourselves. Okay, that is that my questions.
Okay, thank you. First of all, is to increase the power density. We can say the power density.
Yeah, power
To the
density.
power to the volume ratio. Okay, basically, when we talk about power, okay, it's nothing but it depends on the torque and the speed itself. Okay, P equal to omega T, torque, which is the speed itself. Okay, directly increase the power itself, we can simply increase the torque. So as I have showed in the how to say slide previously, okay, initial torque value is something like, let's say, 50 Newton meter. The same size of the machine, okay, same volume of the machine, let's say volume 100 mm, the stack length is 50 mm, okay, the same size of the machine, only we configure all the parameters inside there, so we can improve the torque. So once we improve the torque, there is a correlation with the power itself, okay. The size is almost same, the density, the volume of the motor, the stator, rotor is almost similar. As I mentioned before, we are using 1:35 ratio. So my idea, my how to say, in my understanding, if you want to increase power density or power to volume ratio, we need to increase the torque or the speed itself. So that is my answer. The second thing, what is the facilities that we need to have if you want to develop mass production? Of course, we must have a molding machine. We must have a molding machine. We must have a good laser cutting machine, okay, to do the maybe daily for 1,000 or 2,000 production. But the key point is the market itself. Is the market ready to receive our flat switching machine to be applied in the system? Okay, like I told you, Toyota itself has one of my prototype is able we can find it in Toyota in Japan. But another student, another researcher in Japan also did various design of FSM. They have 100 100 prototype ready, ready with more than 90% efficiency. They have more than 100 prototype ready to be fabricated, ready to be mass production. Currently, they are still using IPMSM in Japan because they have already do the molding system and they make a big factory to mold the machine apply in their motor itself. But to change from IPMSM to the FSM, then they need to start from the beginning again. They need to do the driver controller. They need to do the molding machine itself. And are they ready? If they're ready, then only we can how to say coordinate with them. Otherwise, for the economic, I think depends on the our minister also. All right.
Basically, we must sing everything.
Yeah.
Okay, thank you, Prof, for the answer.
Produce and sell others. Nobody want to buy.
Yeah, thank you, Prof.
Ya. Okay.
Oke, Bro. Kemudian ada pertanyaan dari
Banyaknya
Mas
pertanyaan dari
Nurul ya, mungkin ya. Yang pertama apa tadi? If we use PLDC from market available, what is the parameter most effective efficiency? Itu yang ya.
Okay, the question is about the BLDC. BLDC is readily available in the market, so you can simply buy and use. But if you want to increase the efficiency of the readily made BLDC, okay, which means that it's already made, so it's nothing but you need to control the current, okay, you need to control the current itself. You need to ensure, you need to have the BLDC controller, and you need to ensure that all the current and the sensor detector and the MCU unit work properly. Otherwise, I believe that only a few % of the efficiency can be increased from that. This is for the case of already made BLDC. But if you want to design your own BLDC, so first you have to do your initial design, and then you can use also the parameter optimization. You can set either you want to optimize the power or you want to optimize the the torque, or you want to optimize the efficiency itself. So during the design, you need to focus which one you want to highlight. Okay. But I think there is a question. How much?
Yeah, the last.
No. Before that, there is how much the estimation cost to fabricate a machine. And is it possible a student of master PhD project? Oh, it's difficult because in my case, one single machine I need to have at least minimum of 10,000 ringgit. 10,000 ringgit, I think, I don't know, maybe 30 million. 30
Times
million.
3.
Times 3, I think 30
Yeah.
million rupiah. So it's not possible. You need to have a research grant to do that. And the last question, what makes flux switching machine fundamentally different from conventional permanent magnet or switch reactor machine into a flux pass? Oh, this is the fundamentally different is the design itself. Okay, as I mentioned previously, flux switching machine using the concept of switching, flux switching. Because first we put all the flux sources in the stator itself. When compared to conventional PM, okay, the flux switching has permanent magnet in the stator, while conventional PM is having magnet in the rotor. Okay, it can be either surface mounted on the rotor, it can be either interior mounted inside the rotor itself. But the key point is in conventional PM, magnet is in the rotor. So magnet together with rotor will rotate during the process. But for the case of flux switching, magnet is in the stator. So magnet is static, no movement of magnet. Okay, magnet is static, only rotor is moving. That's why when the magnet is located on the stator, so magnetic from the stator will flow to the rotor. At one point, the rotor receives the plug from the stator, and when it rotates to few degrees, then it brings the flux from the rotor to the stator. So the flux has been changed. The polarity of the flux has been changed from receiving. Receiving, we can say north polarity. Okay, and then bringing to the stator. Now it becomes the south polarity. So the changes of the flux between north to south at the same rotor pole, at the same stator pole, make the flux changes. So that's why it's called the flux switching. So basic to understand the fundamental flux switching is that no magnet on the rotor, okay, flux switch between the stator and rotor itself that make the polarity of the flux changes from north to south, south to north, and so on. That's why they call the flux switching. Thank you, thank you very much for the good question. Is there any other question? Mungkin di sana ada software jamek, Pak Wi. Ada software untuk design motor mesin. Atau ada researcher yang buat design motor di sana di Brawijaya.
Kita tidak ada, Prof.
Wah, mungkin kita bisa collaborate. Mungkin
Ya,
ada kepakaran di sana.
sepertinya kalau Brawijaya punyanya ANSYS, tapi bukan di departemen kami sih.
Oh, mungkin di mana? Mechanical ya?
Iya, mechanical. Tapi
Oke.
itu paket komplit, termasuk ada magnetiknya juga sepertinya. Ada
Ya, ya.
Maxwell, ada banyak. Saya sudah beberapa kali sarankan Pak Wiono untuk agak ya berdekatan dengan teman-teman di mechanical, tapi sampai sekarang kok belum kelihatan.
Masih banyak constraint, Prof.
Mungkin kita boleh collaborate beberapa student di sana yang
Ya.
mungkin buat projek dengan kita di sini. So, jadi kita boleh collaborate, saya boleh bagi free license untuk student, boleh gunakan. Boleh guna online saja pun boleh. Mungkin next time lah kita boleh collaborate.
Ya, boleh, boleh. Sepertinya beberapa student kami juga ada yang interest dengan mesin ya, mesin
Hmm.
untuk motor.
Oke,
Ya,
oke.
studentnya Pak Wi.
Alhamdulillah.
Ya, kebetulan saya concern di electrical machine, Prof.
Oke.
Jadi, ya sejak kuliah di UM tahun
Hmm.
2003
Hmm.
under Prof. Khalid
Prof. Khalid?
Almarhum.
Oh,
Ya,
almarhum. Prof. Khalid is my, I can say, lecturer in UM.
Ya, saya 2003, Prof. Di
Oh,
UM ambil PhD.
saya graduate UM 2001.
2001. Oke.
Mungkin Pak Wei masih kenal sama dengan anak muridnya Prof Khalid.
Iya, kata
Prof, I don't know, Hazli Mukhlis.
Asli, ya, saya ke Malang, sering ke Brawijaya sini.
Oh, oke. Alhamdulillah.
Baiklah, pertanyaan. Kami mengucapkan terima kasih, Prof, atas lecture eh, sesi kedua dari 2 sesi terakhir. Sangat-sangat bermanfaat bagi kami dan kita semua. Semoga bermanfaat juga untuk student kita terutama ini.
Insyaallah.
Kemudian ya, semoga lecture ini masih berlanjut, Prof, the next
Insyaallah.
program.
Hmm.
Kemudian nanti saya sampaikan semua ini ke departemen, termasuk offering Prof, invitation Prof untuk collaboration between Brawijaya and Donusan on University.
Baik.
Nah,
Terima kasih.
kita mau foto bersama, Prof.
Oke,
Ambil
bisa.
gambu bersama.
Oke.
Mau ke
Baik,
Mas Indra?
mungkin bisa di open cam semua.
Ya, tolong open cam.
Kok ada mahasiswa namanya Risyam ini siapa?
Iya, Pak. Salah nama, Pak.
Mas Indra ready ya?
Ini siapa?
Oke.
Iya. Baik, saya mulai. 1, 2, 3. Lagi.
Sudah, Mas Indra?
Eh, sudah, Pak.
Sudah ya?
Sudah.
Oke. Sekali lagi terima kasih untuk para peserta pensyarah dari seluruh Indonesia dan student dari Brawijaya dan university lain. Semoga semua ini bermanfaat bagi kita semua dan kita akan ketemu lagi di next lecture. Terima kasih sekali lagi, Prof.
Ya, sama-sama. Kembali. Jumpa lagi insyaallah.
Ya. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam.
Waalaikumsalam warahmatullahi
Thank you, Prof.
wabarakatuh.
Ya, thank you.